Try this. Pause. Pause. I could have used that a minute and a half ago. Okay, so for the sake of time, I'm just going to kind of push us through. Normally, we'd spend a little more time. I'd walk around the room helping you, but for efficiency, maybe we'll just kind of move on. So, not move on, but kind of move along. Okay, so we've got a function x cubed minus x, 5, let's see, x cubed minus 7x minus 6 over x squared minus 9. Okay, so it says, factor the denominator. What's the domain of f? Investigate the graph of f around x equals 3 to see if f has a removable discontinuity x equals 3. Okay, so the bottom is x plus 3x minus 3. It'd be nice if the top factored, but it doesn't easily. Okay, so that creates a little bit of an issue. But it says, see what's going on at around x equals 3. So if I had that in my calculator, x cubed minus 7x minus 6 divided by x squared minus 9. Okay, so at x equals 3, there's no asymptote like there appears to be at x equals negative 3. That is a vertical asymptote at x equals negative 3. At 3, it looks like there's nothing going on there. Okay, but there still might be a discontinuity because it could be a removable discontinuity. So I'm going to calculate the value at 3, and it tells us nothing. So there isn't a value that the calculator is giving us, so that's an indication that x equals 3 is a removable discontinuity exists at that spot. Okay, so that means there's an x minus 3 factor on both the top and the bottom. Okay, so we already know that there's an x minus 3 on the bottom. There must be an x minus 3 on top also. So we could do x minus 3 goes into x cubed plus 0x squared minus 7x minus 6. We could do it that way, or we could use synthetic division. So this is polynomial division. I don't know if we remember this or not. It's going to happen this year at times. So that's gone 3x squared minus 7x minus 6. Then it goes in there 3x times 3x squared minus 9x. Weird. So subtract, we get 2x minus 6. Oh, I'm not done. Plus 2, 2x minus 6, and we get 0 for the remainder. Couldn't figure out why I wasn't going into it. I just had to keep working on the problem. All right, so we did get 0. That means it's a factor. That means the top factor is to be x minus 3 times x squared plus 3x plus 2. Okay, so since the top factors, we have x minus 3's, they do cross off, and it's apparent that there is a removable discontinuity x equals 3. Anytime you can cross off a factor on top and bottom, there's a removable discontinuity. Okay? Now, on the AP exam, I would about guarantee that you'll have a question about an extended function. So you have to show an extended function for this f of x that makes it continuous at x equals 3. So basically, the original right here looks like that, except there's a hole in the graph right there. Our job is to do the same thing, but plug that hole. Okay, there's two ways of doing it. The most straightforward way would be if g of x is our extended function that plugs the hole at 3, we'd say, well, g of x is the same as f of x as long as x is not equal to 3. But when x is 3, we want g of x to be whatever that y value is right there. We're going to plug it with that y value. So what is the limit of f of x as x goes to 3? So that's like a sub-problem over here. So what's the limit of f of x as x goes to 3 equal to? Any ideas how we could do that? How could I find the limit of f of x as x goes to 3? What are some ways of finding limits? I did make that list with you, right?
You can't do substitution.
Okay, I can't do direct substitution right away, right? Okay, so that, if I was just going to directly substitute right away, that's not happening. What's another way we could do our limit? You could graph it. That's not ideal, right? And table is not ideal. So let's come back to that if we need to. Is there another way we could do, like algebraic manipulation or cancellation, that would work without graphing or using a table? Well, have we factored yet? Have we changed the way it looks? Our new and improved is right here. So essentially, we've been doing the cancellation method. We made this look like this. Now will direct substitution work? Yeah. If I plug in 3, I would get 9 plus 9 is 18 plus 2 is 20 over 6. So our answer is 20 over 6 right down here. 20 over 6, or we'll call it 10 over 3. Okay, we know that the limit exists to be 10 thirds. That's the y value. That ordered pair right there is 3 comma 10 thirds. Okay, so if we want this g of x to be continuous at that point, well, it's going to be the same as f of x, except when x is 3, we want the function to have the value of 10 thirds. Okay, so if you draw f of x with a hole in the graph and then continue it at 3 comma 10 thirds, put a dot right there, then we're done. That's called an extended function. That makes it continuous at x equals 3. Now it's not continuous everywhere because there's an infinite discontinuity at x equals negative 3, but the question was to make an extended function continuous at x equals 3. Okay, I told you there's 2 ways of doing it. There's one way. A second way, g of x could be, well, this g of x was f of x and then plugging it. If I go back to this red one, this special red one, this is literally the same thing as this g of x. Okay, because this function doesn't have a hole in the graph at 3 comma 10 thirds. We eliminated that hole by crossing off the common factor. So another answer for g of x would be just whatever function you ended up getting when you eliminated the factor of x minus 3 on top and bottom. So these two are literally the same thing. Either one is acceptable. Sorry, it wasn't on the screen. I was pointing as if you can see it. So this function and this function are the same thing. On the AP exam, they should accept either one. This one's a little cooler. It's actually easier than going through this whole process. But sometimes you can't do it using factoring. Like if I asked you to make this function continuous for all x, well, what's the one place it's not continuous? At 0 comma 1. Very good. So if I wanted that to be, plug the hole right there, our function, we can't factor that and cross stuff off. We literally have to just say, well, it's sine x over x for x not equal to 0, but when x is 0, we want it to be 1. Now it's a continuous function. Okay, questions on that? The other thing with continuous or continuity, if we've got a function like this, the composition of functions, so x, just the function y equals x is a continuous function, it's just a line. Sine x is just a curve and it's continuous. If you multiply two continuous functions, you still have a continuous function. Divided by a parabola, which is continuous. And if you take the absolute value of a continuous function times a continuous function divided by a continuous function, it's still continuous. Okay, so that's the only point there, that it remains continuous if you multiply, divide, or take the composition of two functions that are continuous. All right, intermediate value theorem. I see it in the book. I might as well show it to you right here. You're going to learn, let's see, I've got 3 minutes to do this one. Otherwise, I'm going to need a new video. Okay, so the notation in a math textbook and a calculus book is confusing. It's something hopefully you get better at. If you're in college taking a Calc 2, Calc 3 class, a lot of times you're going to have to learn what all of this means on your own. But I'll give you a little bit of help. The intermediate value theorem states in, boy, that prior to the AP exam last year, we did a whole series of AP reviews, and they loved the intermediate value theorem on their reviews. I don't remember if it was on the AP exam, but the intermediate value theorem states basically in, a real life terms, if I've got, now I have 2 minutes. Let's say I've got a little boy. He is 5 feet tall. There he is. Pretty proud of his 5 feet height. Okay. Later on in his life, he gets to be 6 feet tall. Now he's 6 feet tall. Do you think that there is a point that he was 5'8"? You pretty sure about that? I would say so, right? It's guaranteed. Why? Because your growth is continuous and it will hit every point along the way. And that's called the intermediate value theorem, that if we have a continuous function, every y value between one point and the next has to be represented. And a lot of times they're across the x-axis. So let's say some function is defined to be continuous. That's important. So is it continuous? Yes. And let's say f of -2 equals -5. I'll just say that's -5. And I also know that f of 3 equals 4. This is 3 comma 4. Do you think there's a point somewhere along the way that this function crosses the x-axis? Okay, so it seems obvious, but we use this to prove things or support our things. So yes, it would have to be. You could assume not. You could assume it doesn't, but then there's no way it could ever get up there. So it could do all sorts of funny tricks. But ultimately, if it's a continuous function, it has to cross the x-axis in that interval. It's important to know that it's in that interval. Okay? All right, that's enough of that video.